All right, we can move forward. We have a second talk, still about blockchain. This is the blockchain session. The title of the talk is Redacting Blockchain Without Exposing Chameleon Hash Collisions. It's a joint work of Thiago Astrizi and Riccardo Custodio, and Thiago will give the talk.
Good afternoon for everyone. First, thank you for your presence. I will talk and present about the paper that I published in this conference. And well, first of all, I think I will give some background and also explain a little the title. The first question that someone could have is, why redacting a blockchain? Aren't the main selling points of blockchains that they are immutable? If you build a blockchain, it's because you want to have immutable data distributed between several computers. But the question is that the problem is that if the data is completely immutable, sometimes this can open you to some problems or attacks. For example, someone could upload illegal content in the blockchain, for example, and so because of this, users could become afraid of storing copies of your blockchain, or because they would be violating some laws if they do so, or in some scenarios, you could need to remove something to comply with some decisions or the judicial decisions of to comply with the law. Another scenario is when you would like to, for example, compress old blocks to make your blockchain occupy less space. So these are the scenarios where sometimes could be interesting to redact the blockchain, but usually is in exceptional circumstances to deal with some unexpected problems or when you have very old blocks. And well, if you want to redact or change a very recent block, usually you could redact the block rebuilding the most recent blocks in the blockchain. But if you want to change or redact something, a very old block, this is not a practical approach. So how can someone do this? Well, in the literature, there are two main approaches about how you can build a redactable blockchain to make these things. The consensus-based reductions, it's when you usually have in your protocol some sort of method to where users can propose reductions and can vote for them. Is one of the methods, but our proposal and our work is about the second technique. That is the techniques based in chameleon hash reductions. Well, for the first of all, what is a chameleon hash? Basically, a chameleon hash is a hash function, but with a public and private key associated. With the public key, you can compute the hash of a message given some sort of randomness, and you produce a digest. If you have the secret key, you can compute collisions. Given any message, you can choose any message to collide with a given input, and it produces a correct randomness so that it will the second message will collide with the given input. And using this the kind of primitive, it's possible to create reductible blockchains. The most basic reductible blockchain would be just replacing the hash function that links each blocks by a chameleon hash function. This way, each block, instead of its contents, also stores the chameleon hash randomness. So you can compute the digest of each block with its content and with the randomness. And then, in this example, we could have a malicious content in block B1 with its given randomness, and then a part which knows the secret key of the chameleon hash could then use the secret key to compute a new message, C1, that collides with the previous block. C1 is a new block with the malicious content, and then it can replace. The idea is that after the reduction, this party that knows the secret key, the trapdoor, can then broadcast the message that a block was redacted to all the participants. And well, if the well-behaved participants that want to also comply with the reduction can then replace the previous content B1 with C1, and then they will not have the problematic content that they had before. Of course, we do not enforce the reduction for all the participants that have the copies of the blockchain. So the idea is that this kind of reduction is more, for example, if you want to compress the blocks, for example, to make your blockchain occupy less space. Or, for example, if you have malicious content stored in commented areas of smart contracts and cryptocurrencies, for example. In these cases, you give the options for well-behaved users to erase the illegal content or the problematic content. And but if some users do not comply with the reduction, in the end, it will not. You are not changing the cryptocurrencies transactions or some things like this. So in the end, all copies of the blockchains will store the same transactions. It is more for these kinds of scenarios. This techniques is not new. It's already exists, but there is a problem. It's not very easy to implement this with a traditional blockchain, with a traditional Chameleon hash that I presented in the previous slide. The main problem is that Chameleon hashes usually they are collision resistant, like any hash function. But the problem is that for most implementations, the collision resistant is a little fragile. For most Chameleon hashes, you can, using the trapdoor, to compute collisions, but you cannot guarantee the security of them if you show the collisions for other persons. The idea is that presenting sample collisions of Chameleon hashes usually weaken its security. In several of them, with sample collisions, attacker could even discover the secret key, for example. And this is a big problem for most Chameleon hashes. In fact, we have only a single Chameleon hash construction that in the scheme that I presented before, that we can show collisions and it would retain its collision resistance. But the construction, the security proof, is in the non-standard model, uses the generic group model. And it's only a single construction linked to the discrete logarithm problem. So it's not a post-quantum construction, and it's to link it to a single construction. So how can we deal with this? In the literature, what the proposals that we already have is do not use the traditional Chameleon hash that I presented before. We use some alternative schemes, alternative descriptions of Chameleon hashes. For example, we can have a secret coin Chameleon hash. The difference of this scheme, for example, from the previous one, is that now we do not control the randomness in this kind of Chameleon hash. We just pass the message, that blue envelope with the public key, and then this computes the digest, to which I'm representing as a fingerprint in the drawing, and it also outputs a proof that this indeed is the digest of the given message. We can use the proof and the digest in a verification algorithm, and then to compute a collision, we could just present a new alternative message with the input of the previous input, and then the collision algorithm will present a new proof that given the red message and the new proof, the verify algorithm will show that this indeed proves that that digest is the digest of this red message. Even if in the beginning that digest was computed with that blue message. This is possible. This is quite usually used in the literature, but the problem is that these alternative chameleon hashes usually is more expensive to use. To build something like this, usually what is done is mixing hash messages or traditional chameleon hashes messages with public key encryption and non-interactive zero-knowledge proofs. And this works, but it's more expensive. While in the more traditional chameleon hashes, we have a very fast construction with constructions that are as fast as computing a SHA-2 algorithm, for example. But with this kind of construction, usually it takes more time to compute, it's more expensive to compute. Usually you spend more time in generating and checking the non-interactive zero-knowledge proof used to check and to compute the proofs. So what we were thinking is, what if we could use the traditional chameleon hashes, where we have more fast constructions? The problem is that if we redact the blockchain with them, we will reveal collisions, and this is a problem. But what if we could build a blockchain linked differently, where we could use the previous chameleon hash, the traditional ones that do not require these proofs and to compute them. If we could redact without revealing the collisions. And so we started to check what properties we could use to build this. Well, one thing that we noticed is that in practice, several constructions of more traditional chameleon hashes has an alternative properties. Not all of them have, but several of them have this property that they also have a pre-image algorithms. Given its secret key, its trapdoor, and given any digest, we can choose any message and it outputs a randomness. Using this randomness to compute the hash with this red message, we could obtain any sort of digest that we chose before. In practice, what this does is compute the first pre-image, not the second pre-images as we had before. It's not a difficult property to have. There are several chameleon hashes with this property. And so we started to think, how could we use this property to build a blockchain? And what we found is this, or is our proposal. Now we also have all the blocks of the blockchain. We are linking them with a hash, as we always were doing before. But now our hash, there are two differences. Now we are differentiating between the non-redacted blocks and redacted blocks. This kind of blocks are different. They are marked differently. And we also link them differently. The idea is that in the beginning, we have a blockchain. All the blocks are non-redacted. We never changed any block. And so all of them are linked with a hash. In this case, our hash is computed, combining first computing a chameleon hash with the content of the previous block, and then taking this output with the randomness and applying this at a usual hash function. So we are composing two hash functions, a chameleon hash and a hash, to generate our digest. And this is the digest that we use to mine the blocks, if is the case. And also, this is the digest that we use to link the blocks. This is the digest that the next blocks stores to link it to the previous one. And but what if we want to redact a block? Then, in this case, we are redacting the block B1 with malicious content or something like this, and replace it with C1. For this, we use the pre-image algorithm. The idea is that in a redacted block, we link it differently. Instead of computing the composition of a chameleon hash function and a hash, we just using the chameleon hash. So, if we want to redact this block, we need to just replace the content B1 to C1. And then we need to discover a randomness to make the hash work. And so what we do is we do not use a collision algorithm. We use the first pre-image algorithm to discover the correct randomness that we use, so that the chameleon hash will give the same result than we had in the usual hash before. This way, we are reducting the blockchain. We are using the traditional chameleon hash, but we do not reveal collisions, because we do not reveal the collisions when we do the reductions. We are just computing a pre-image from a value that is not related with directly with the output of a previous chameleon hash that we had before. And this is the main idea. With this, we could just need this pre-image algorithm, and we had just checked that we also had needed another property that if we have a pair of a randomness and a digest, an attacker must not be able to distinguish if this pair was composed first from the randomness to compute with the hash the digest, or the other way, from the digest with the pre-image compute the randomness. The idea is that we cannot distinguish how this pair was obtained, which is also not a difficult property. This property that we have several chameleon hashes that have this. And so what we did is check it first. We checked our times to see how fast we can do using our ideas with faster traditional chameleon hashes that we had before. This in green is a regular blockchain, a non-reductible one. This is the time is how long it takes in milliseconds in the tested machine to compute a SHA-2 hash over a 1 megabyte block. And this is a lower bound. Probably you cannot compute the hash in a reductible blockchain faster than this, because this is the timing in a non-reductible traditional blockchain. This is the faster than we had before. If we had used the only traditional chameleon hash that could be used before, if you allow a non-standard security proof in the generic group model. This is the faster than we had before. This is if you want more options of chameleon hashes using the secret coin chameleon hashes, using non-interactive zero-knowledge proofs. This we used a construction proposed 2 years ago, very recent, that achieved very high a full collision resistance, and it's lower, but you had a construction more generic, and that you could use more options of algorithms. And now, in the light gray area, is retesting our proposal with existing traditional chameleon hashes that are faster. First, this is a construction proposed by Mihir Belari, a chameleon hash that uses computing a hash means computing about 128 multiplications of big numbers roughly of the size of an RSA key. It's using the factoring assumption. Well, we had a very similar time with what we have faster before, but in this case we had a proof in the standard model. But that article that proposed this construction from Belari also proposed an optimization in the chameleon hash, but you had to trust a stronger assumption that computing modular square roots of small primes modular composite number is hard. And then we could finally have a timing, a faster time that we have before. And then this is constructions using post-quantum chameleon hashes to have a post-quantum reductible blockchains. This is based in the ring-size assumption, Well, it's a little is lower, but it's comparable to with what we had in a classical non-post-quantum construction based in the secret coin Chameleon hashes. And this is a very recent construction proposed about 3 years ago of a new Chameleon hash, a post-quantum one, which is very similar, related to the Falcon signature scheme. Basically, computing a hash here is very similar to verifying a Falcon signature, and computing a pre-image is very similar to computing a Falcon signature. And it achieved a very fast timing here. And it's a post-quantum construction, and it beat the previous construction, the previous timings that we tested before. Not because our proposed blockchain, reductible blockchain, is per se faster, but the fact is that our proposed construction allows us to use a greater variety of Chameleon hashes that we could before. These Chameleon hashes we could not use before because reducting would reveal collisions. But if we remove this, if we reduct it in a way that we do not reveal collisions of Chameleon hashes, then we could use them, these constructions, and that are faster, and then we can achieve faster times. And this is our article, and now I'm open to questions. Thank you for your attention.
Thanks a lot, Thiago, for the presentation. We have time for questions. Okay, let's start. You need a microphone? Okay, it's coming.
Thank you for nice talk. So about this generic group base, I think they are based on the interactive branch proofs that you mentioned, based on the snarks. So if I remember correctly, they are built based on the first simulation extractively snark. Have you checked that, or?
Sorry, could you repeat again?
Yeah, the second construction that you mentioned, generic group model base. Yeah, this one, the second one. Yeah, this was based on the first snark that was non-malleable, because we need non-malleability because of...
Sorry, you are talking about the red one?
Yes, the generic group base.
No, this is a construction proposed, it's a very old construction proposed by Atrizi and Medeiros, this based in the generic group model, and it's basically in the end in the discrete logarithm problem, but it assumes that you need to use the assumption that the encoding of the elements of the group do not reveal any information about its content. You assume that each element in the group is randomly encoded. This is the assumption that you need to make to assume that this is safe. And it's very deeply linked with the discrete logarithm problem.
Okay, then maybe, have you checked the new constructions from 2020 or something?
Oh, I think...
that are using universal ZK snarks, that they have succinct verification. So you criticize that the timing is slow, but the point is that you don't redact the blockchain frequently. You just do it a few times. Oh. But on the other side, the proof is very succinct. The verification is very fast, millisecond. So I don't entirely agree with the criticize that non-interactive ZIP based on reductible blockchains are not efficient. You mentioned in the presentation. So I thought this is based on snarks, but if you said it's not?
No, it's not new. This construction is, but we will check the article that you mentioned in the books.
Okay. So thank you.
Thank you for the answer. Are there more questions? I have some, but first I prefer questions from the audience. Okay, so I have one or maybe more questions. Where is the secret key? Who knows the secret key that is required to redact the blockchain?
Well, when you basically when you use the Chameleon hash, you have a key generation algorithm, and it produces a public key and a secret key. And then to redact it, you use the Chameleon hash secret key.
So
the hash key.
Let me repeat the question. Who runs? What is the party, the entity that runs the generation of the keys and therefore has the secret key in the pocket. Which player?
With
It's a miner?
who has the secret key?
Yes.
Yes.
Miner or I don't know.
Oh, yes. Good. Yes, this. Well, the idea is that in the idea is that in the blockchain, when you are building, you could choose some trusted party or that could have the key to redact in exceptional circumstances. But the idea is up to the construction of the blockchain. I think that perhaps this is more interesting in the private blockchains because in this kind you anyway have some degree of centralization, some sort of entity, and they could have someone with the keys. But also there are other options. There are some possibilities with chameleon hashes that you could, for example, have more than one party with the shared key, and then with more than one party agree with the redaction, they could redact. But there are choices that can be made when the blockchain is being built.
Thank you for the answer. Maybe if we can a little bit dig in this direction, because I mean, if the secret key is known only by one player, then this player, it's a single point of failure, which seems to be against the paradigm of decentralizing, right? If it's in the case of a permissioned blockchain, then there is a community of fixed players that are in charge of the governance. But in that case, you cannot give the secret key to all of them, because then just one of them can again redact on his own. So that must be then a secret shared among the players. But this analysis is about threshold, chameleon hashing, in the sense that if you secret share the secret key, then to do a redaction, you need a more complicated protocol, because, right? So this analysis is for the case where the secret key is secret shared, or for the case where there is one player with the secret key in the pocket. Just this is my question.
Well, sorry, could you repeat the end of the question?
Yeah, the end of the question is the following. The analysis that you show the timing here.
Yes.
It's with one player having the secret key, or with the secret key shared among multiple players.
Yes. What we assumed here is one player having the secret key. But in the in the end, it was we considered it outside the scope of the paper, and for further works to study better how to deal with some complications. Like, for example, you need in some scenarios to revocate the key. And for example, I say that you do not review collisions, but only assuming that you redacting each block a single time. There are some cases that you could need to redact more than one, and so you could need more than one key, some sort of revocation. And yes, there are some further works that could expand over this that need to be addressed. But I think that this is a disadvantage of the kind of redacted blockchain based on chameleon hash. You really need a central authority. There is some centralization. This is a disadvantage. But they have also the advantage that when you really need to make a change, for example, because the law says that you need to do, you can make it instantaneously. Do not depend of the parties voting or something. And so you have these advantages and disadvantages.
Thanks a lot for your answers. More questions? Yeah, we still have one. Yeah, we have 2 minutes. Yes, go ahead.
I'm wondering if your constructions, this pre-image algorithm that you have, also your constructions guarantees that after running this pre-image several times, still an adversary cannot use these outputs and generate a new one.
Mm-hmm. Well, the idea is that I think that it's because of this that we needed that strong uniformity property. The idea is that the computing the pre-image and generating randomness will not reveal information for attackers, but we really need that strong uniformity property because of this. Not only the first pre-image resistance. If you have this property, you can run the pre-image algorithm several times, and the randomness that will be generated will not reveal any information, because it would be not different that a randomness generated in the first scenario randomly.
So thank you. I think we should really thank again Thiago, because has been very kind answering all the questions. And now,
Thank you.
now we have the poster session, lightning talks.